Hello again. This is the second in the three-part series leading up to the law of quadratic reciprocity. The link to the first and the third are in the description. In this video, we turn our attention to what is known as Gauss's lemma. Gauss's lemma provides us with an alternative method of determining whether the number a is a quadratic residue modulo p. In contrast to its counterpart, Euler's criterion, Gauss's lemma has a lengthier phrasing, but what it lacks for in simplicity, it makes up in applicability. Here is the statement. Let P be an odd prime and let the GCD of A and P be 1. Then the Legendre symbol A upon P equals negative 1 to the power n, where n is the number of elements in the set S equals A, 2A, 3A and so on all the way up to P minus 1 upon 2A, that on division by P leave a remainder that is greater than P upon 2. Transiting to our proof, we first create the required notation to ease communication on the topic. Of the P minus 1 upon 2 remainders, let R1, R2 all the way up to Rm be the remainders of the elements of S on division by P that are less than P upon 2, while S1, S2 all the way up to Sn are the remainders of the elements of S on division by P that are greater than P upon 2. It is important to know that none of the elements in S are multiples of P. The condition that the GCD of A and P is 1 in conjunction with the fact that Ka is congruent to 0 mod P leads to K is congruent to 0 mod P for K between 1 and P minus 1 upon 2 inclusive, which is wrong. The SIs and RJs are all different from each other, no two being equal. This is since the GCD of A and P equals 1, and so the condition Ka congruent to Ja mod P for K and J between 1 and P minus 1 upon 2 inclusive leads to the requirement that K is congruent to J mod P for distinct K and J, which is ludicrous. In making the leap towards the final step of the proof, all that remains to be shown is that none of the values of P minus Si are equal to any of the Rj for any I and J. Notice that P minus Si is less than P upon 2 for all i's. To prove the statement we have made, we hunt for a contradiction. Say Rj equals P minus Si for some I and j. Then let u comma v between 1 and P minus 1 upon 2 inclusive be the numbers such that Si is congruent to ua mod P and Rj is congruent to Va mod P. We also have that Si plus Rj, which equals P, is congruent to 0 mod P. Digging deeper, we see that u plus v into A is congruent to 0 mod P, leading to u plus v is congruent to 0 mod P, which is impossible as u plus v is strictly greater than 1 and strictly lesser than P minus 1. We are now fully equipped to prove Gauss's lemma. We consider the product R1, R2, R3 all the way up to Rm multiplied by P minus S1, P minus S2, P minus S3 and so on all the way up to P minus Sn. Reducing this modulo P, we have that it is congruent to R1, R2, R3 all the way up to Rm into negative S1, negative S2, negative S3 all the way up to negative Sn, which is congruent to negative 1 to the power n into R1, R2, R3 all the way up to Rm into S1, S2, S3 all the way up to Sn mod P. But we know that the numbers Rj and Si are essentially congruent to the numbers A, 2A, 3A all the way up to P minus 1 upon 2A in some order. Hence, we know that minus 1 to the power n into R1, R2, R3 all the way up to Rm into S1, S2, S3 all the way up to Sn is congruent to minus 1 to the power n into a to the power P minus 1 upon 2 into P minus 1 upon 2 factorial. But we also know that all the Rj's and P minus Si's are distinct and all less than P upon 2. Therefore, they must exactly be the numbers 1 to 3 all the way up to P minus 1 upon 2 in some order. This is since the total number of Rj's and Si's are equal to P minus 1 upon 2. R1, R2, R3 all the way up to Rm multiplied by P minus S1, P minus S2, P minus S3 all the way up to P minus Sn is congruent to P minus 1 upon 2 factorial modulo P. Summarizing, we are left with minus 1 to the power n into a to the power P minus 1 upon 2 into P minus 1 upon 2 factorial is congruent to P minus 1 upon 2 factorial modulo P. Since P minus 1 upon 2 factorial is co-prime to P, we can reduce this to minus 1 to the power n into a to the power P minus 1 upon 2 is congruent to 1 mod P. Multiplying both sides of the congruence by a minus 1 to the power n, we see the fruits of our labor in the expression a to the power p minus 1 upon 2, which is congruent to minus 1 to the power n mod p. As in the proofs of the properties of the Legendre symbol, this congruence translates to an equality. This is because a to the power p minus 1 upon 2 is either congruent to 1 or negative 1 modulo p. The RHS is also either 1 or negative 1. If they were not equal, we would find ourselves staring at the statement 1 is congruent to negative 1 mod p, implying that p divides 2, which makes little sense as p is taken to be an odd prime. Therefore, a upon p equals negative 1 to the power n, and we are done. With this expose of Gauss's lemma complete, we can now engineer the final tool required in allowing us to prove the law of quadratic reciprocity. This final tool is an extension of Gauss's lemma, but it's limited only to cases where a is an odd number. In such cases, we have that n is congruent to the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of ka upon p mod 2. Thus a upon p equals negative 1 to the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of ka upon p. N and the summation of integral parts on the right hand side are either both even or both odd. So, as the exponent to negative 1, they result in the same value. In essence, this allows us to shift our focus from the study of remainders to finding the integral parts of improper fractions and then summing them up over a range of k values. This is the extension of Gauss's theorem. Its proof requires heavy lifting, but in the end, it is worth it. We begin by recalling the set S equals a, 2a, 3a all the way up to p minus 1 upon 2a. Now, subjecting each element to the division algorithm with p, we see that ka equals qk into p plus tk, where tk is either some rj or si. This is true for each k between 1 and p minus 1 upon 2 inclusive. With the aim of trying to find a general expression for each qk, we divide both sides of the relation by p, yielding ka upon p equals qk plus tk upon p. Now taking the greatest integer function on both sides and noticing that tk upon p is strictly greater than 0 and strictly less than 1, as all the remainders are less than p and greater than 0, we get that qk equals the greatest integer part of ka upon p. This allows us to write the expression ka equals the greatest integer part of ka upon p multiplied by p plus tk. Taking the sum of the equation of the p minus 1 upon 2 values of k for which it applies, we extract the statement, the sum as k goes from 1 to p minus 1 upon 2 of ka equals the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of ka upon p multiplied by p plus the sum as j goes from 1 to m of rj plus the sum as I goes from 1 to n of si, which we name equation 1. Here we use the same notation as was used in the proof of Gauss's lemma. Notice how each of the tk's are either si's or rj's but not both. Also, m plus n is equal to p minus 1 upon 2. But we even know that as all the rj's and p minus si's are distinct and are equal to the numbers 1 to 3 all the way up to p minus 1 upon 2 in some order, we can conclude that the sum as k goes from 1 to p minus 1 upon 2 of k equals the sum as j goes from 1 to m of rj plus the sum as I goes from 1 to n of p minus si, which equals the sum as j goes from 1 to m of rj plus pn minus the sum as I goes from 1 to n of si. Let us call this equation 2. Subtracting equation 2 from equation 1, we have a minus 1 into the sum as k goes from 1 to p minus 1 upon 2 of k equals p multiplied by the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p minus n plus 2 times the sum as I goes from 1 to n of si. Reducing the statement modulo p, as we only care about the evenness and oddness, we get that p into the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p minus n is congruent to 0 mod 2. This is because a minus 1 is even, and so a minus 1 into the sum as k goes from 1 to p minus 1 upon 2 of k is congruent to 0 mod 2. 2 into the sum as I goes from 1 to n of si is definitely a multiple of 2. and so it too is congruent to 0 modulo 2. Now 2 does not divide p as p is an odd prime. Therefore it must be the case that the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p minus n is congruent to 0 mod 2. This ultimately leads to the statement that n is congruent to the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p modulo 2, which was the goal of our endeavor. Thus we can write that the Legendre symbol a upon p, which equals negative 1 to the power n, also equals negative 1 to the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p, as the quantities n and the sum as k goes from 1 to p minus 1 upon 2 of the greatest integer part of k upon p are both even or both odd. Now we find ourselves at the point where we have learned all the necessary prerequisites to understand the law of quadratic reciprocity and its proof. Follow along on the third and final video of the series to see how we use Gauss's theorem and its extension to prove the law of quadratic reciprocity. As a short postscript, and something that I have already mentioned in part 1, all the credit for the proofs and theory goes to David M. Burton, who is the author of the book Elementary Number Theory. In addition, credit is given to McGraw-Hill Education India Private Limited, who have published the Indian edition.